Hello. Okay, so good evening everyone. I am Shagnik Rai, a final year BSc student at Presidency University. It's my great pleasure to tell you all that today we kick off Precision 2022, the Physics Fest of Presidency University. We start with a plenary talk this week and the next events in the coming week. So without further delay, now I would request our honorable faculty, Dr. Susthana Chatterjee, without whose effort this event wouldn't be possible, to share about how Precision started and its journey.
Thank you, Shagnik, for the kind words about me. And it's definitely a great pleasure for me that we again resume Precision in offline mode after 2 years, after the horrible 2 pandemic years. So Precision that our students organize at their academic fest every year is something that is very, very, very dear to my heart. So I'll tell you the story. This was 2017 when we were celebrating our bicentenary year. And today's speaker, Arijit Shah, he was at that time a second year student, and their batch was the first batch, and all these people, Arijit and his colleagues, his friends, they were the mastermind behind Precision 2017. That was our first Precision. Now, when the discussions were going on, so the university gave a handsome fund for this event. And when this discussion was going on that what can we do? Oh, we can have this, we can have that. And then that was the first time that's the main person, the person who worked most for Precision and was the chair of the LOC, Shauradip Bhattacharya, who is now a graduate student at Ohio State University. So Shauradip and Arijit and many other, all his colleagues, Shomendra, Rutushabho and others, Shagnik, Shogato. So I just told them that, look, folks, this is a chance of a lifetime. We are celebrating our bicentenary year, and you are starting as the year of your academic fest. So we have to do something that has not ever been done in India. Because I always had this dream when I went to the US for my graduate studies. I always had the dream that if I come back to India ever as a faculty member, then I will introduce, I will just try to introduce undergraduate research and combine research with teaching. And by the year 2017, we were successfully doing that at Presidency University. 2016, 2017 were the first years of our success when our undergraduate and master students started doing research and started publishing their first papers. Okay, so my first paper with Dhruvo, who was a colloquium speaker at SOA a few weeks back, came in 2017. So that was my first. So that was the time when we were already on the verge of making this dream, making my dream, I would say. I'm so grateful to our students that I could get such students with whom I can share my dream and make them fruitful and possible. So then I told them that, look, in the US, it's very common to have this undergraduate research symposium, research meet, where it is organized by the undergraduate students, the speakers are the undergraduate students, and it's like a conference. And I think the other person who like wholeheartedly supported me and told me, Suchasana, why don't you tell the students to do a research meet? And that was Professor Parthasarathy Majumdar. Some of you have met him. He was once or twice, he was in a colloquium. He was at that time teaching Arijit's batch and some other batches. So this was just Professor Majumdar and I, we pitched and said we should convince the kids to do the undergraduate research symposium. And that was, and we told them, and as I said, that I think my privilege is that I got students with whom I can not only share my dreams, because you really have to be very lucky to have people with whom you can talk about your heart's desires. You all know that, right? Not your thoughts. But my students have been terrific, and they are terrific till now. That's what we are seeing. So then we had the starting of the undergraduate research symposium. I said, you have to have an SOC, you have to have an LOC, this is how you have to do it. I'm going to publicize this for you, but take the lead. And then this remarkable thing happened. This was March 2017, when we had our first Presision. And then it was a phenomenal success, and then it grew over years to the extent that we had speakers from ISARS and IISc from outside of West Bengal coming to our undergraduate research meet. And then when the students organized that in the online mode, there were even international speakers. And of course, our students graduated from our program and went outside for PhDs, went outside of Bengal and went outside of India for their graduate studies, and hence the network started growing. Okay, and Presision and the research meet became like super success. The other thing I told in 2017, I expressed interest to our students that, look, they were saying that we'll have a public lecture. I said, yeah, from a scientist and all that. I was like, look, people hear lectures from scientists all the time. You are going to invite school and college students. Why don't you think of giving a peer public lecture? And one of you will be giving the public lecture. And they said, us, how can we will have give the lecture? And I said that, oh yes, that's what make people happier, because they connect. When a school student sees that, okay, the dadata, didita, who is only a couple of years older than me, can give this lecture, that makes them happier. Because when they look at a scientist or a faculty, they think that they are way ahead of me. And so that's a dream that is, many years down the line. That's not something I can immediately reach or inspired from everybody, but we get a different kind of inspiration from our elders and a different kind of inspiration from our peers. So that was the first public lecture that started from a student, and we had Kaustav Mitra, whom some of you met, particularly the PG2 students met, because he gave lectures to you on structure formation, who's now a PhD student at Yale University. So Kaustav was our first student public speaker, and I'm sure several of you have experienced the wonderful talks that all these years our students, our alumni students, and our current students have given as public talks. So it is again my great honor that I got to speak in Presision 2022, thanks to Shadmik and others who are in the organizing committee, and be present to the public lecture. This is the 6th year, 2017, 18, 19, 20, 21, 22. So the 6th year, and this is again a great pleasure that we have Arijit giving the talk, who was again among the group of people who conceptualized and started Presision. So without taking further your time, I really want to welcome Shadmik again to further continue the program. And thank you very much for organizing this, and thank you very much for coming on a Saturday to enjoy and celebrate the spirit of Presision. Thank you.
Thank you, ma'am, for your kind introduction. So now I would like to request Moitroda to come and chair this session.
Okay, thanks a lot, Shagni. So, good morning, everybody. And so, this public lecture officially kicks off Presision 2022, and This year, Precision is being organized for the 6th time, having first been organized in 2017. You heard all the history from SCMM just now. So today our speaker is Mr. Arijit Shah. So Arijit did both his bachelor's and master's from Presidency. He was in the class of 2018 for his bachelor's and 2020 for his master's. And now he is also now a junior research fellow at the same department here. And he is now working in an ISRO-funded project under Dr. Ritoban Chatterjee, where he is working on some exotic astronomical objects called active galactic nuclei, taking the help of India's first dedicated astronomy satellite called AstroSat. So in fact, those are the very things that he will be talking today, and I'm sure that we will get a glimpse of how interesting these things are. So without further ado, I would like to invite Arijit to the stage.
Thank you, Moitro. Thank you for that kind introduction. And thank you to everyone who has turned up today for this 6th year of Precision. As SCMM mentioned, in 2017 was our batch. We are the 2nd year bachelor students back then. So under SCMM's guidance, we took the initiative to start this Precision Physics Summit, which was the first of its kind in India that incorporated a undergraduate physics symposium, right? So where all the speakers, all the organizers, all the chairs, everyone was an undergraduate student, right? So this is pretty unheard of in India. So I vividly remember in 2017, the night before Precision, we were huddled up before the Baker Laboratory gate. So we were, very tense. So tomorrow is Precision is starting. Okay, so we need to organize. Okay, so who is organizing the food? Who is organizing the water? Who is organizing this? Who's organizing that? So it was we were tense, but it was extremely enjoyable. And it turned out fine. It turned out more than fine. It turned out mighty fine, right? So, and it's nice to see that 6 years later, it's still going strong. So I've been told to talk to you. So what I'm going to talk about is India's first multi-wavelength eye in the sky, a new perspective on active galaxies. So when you hear the word eye, so think about this. Humanity has been on this planet for a long time, right? And whenever a human being has looked up at the sky and wondered at the majestic universe, right? So every time we have looked up, we had to use our own eyes, right? But in the 21st century, that is no longer the case. Now we can build huge eyes, right? Telescopes, and we can even send them into space. And that is exactly what India did 7 years ago with the launch of AstroSat, India's first multi-wavelength satellite. So AstroSat will be the main focus of this talk. And at the end, I'll try to talk a little bit about what active galaxies are and what we can learn about active galaxies using AstroSat. Right? Okay, first things first, the plan for the talk. So every good movie or play is a 3-act play or a 3-act movie, right? So I've tried to design this talk as a 3-act talk. So the Act 1, we'll learn about what multi-wavelength astronomy is and why we need multi-wavelength astronomy. In Act 2, we'll be introduced to AstroSat and the impact AstroSat has had on Indian astronomy and particularly young astronomers. This is ultimately an undergraduate physics symposium, and it's very important to understand what the effect of AstroSat has been on undergraduate and graduate researchers in this country, right? We'll also discuss some of its important achievements and results. And finally, in Act 3, we'll talk about what active galaxies are and what we can learn about active galaxies using AstroSat. I'll try to snuggle in some, research that is done on active galaxies here at Presidency. So we'll see how it goes. Okay, Act 1, the Great Revolution, the space age and the advent of multi-wavelength astronomy. So, okay, when any of you go outside and look up at the sky, what do you see? Well, you don't see much in Kolkata, obviously. Kolkata has a terrible condition to see, look up at the sky, right? You can only see barely a few planets or a few bright stars. But if you could go out to a dry region where there is no light pollution, no air pollution, so what would you see? You'd see something like this. You'd see thousands and thousands of stars, right? And they are of different sizes, of different brightness, right? majestic view. And if you're lucky, you could see actually what is there in the middle, a thick band of cloud and gas cloud and light coming in a thick band, right? Does anyone know what this is? Yes, this is the Milky Way. This is our very own galaxy, and this is not a fake image or something, right? This is an actual image taken in the Black Rock Desert in Nevada, right? So think about this. When you are looking up at the sky, you are seeing your own galaxy that we didn't even know about properly 100 years ago, right? So people thought Milky Way was the whole universe. We learned that Milky Way is only one of the billions upon billions of galaxies that are present in our observable universe, right? So this majestic view that you are seeing, this is great, but this is nothing. Why is this nothing? Because when you look up at the sky, you're only able to see in the visible spectrum or the optical band, right? And the visible or optical band, we all know about the electromagnetic spectrum. Think about how huge the electromagnetic spectrum is. From down to long radio waves and up to gamma rays, it's about 25 orders of magnitude. Just imagine, 25 orders of magnitude. And we're only limited to 400 to 700 nanometers. That is nothing compared to the whole electromagnetic spectrum. The rest of the electromagnetic spectrum is completely invisible to us, right? So why is the electromagnetic spectrum, the whole electromagnetic spectrum, not visible to us? Well, most of it is because of our sun. So if we all know that our sun is a very good approximation for a black body, right? And if you had to measure the solar radiation down on Earth and plot the spectrum, it would look something like this. So the yellow is measured above the atmosphere and red is at the sea level. So if you look at the red spectrum, see where it peaks. It peaks around 500, 600 nanometers. And that is exactly in the visible range, right? So naturally, most of the light, if the most of the light is coming to us in the visible spectrum, all the animals on this planet, including human beings, have evolved to make use of this fact and absorb and try to see in the visible light, right? Also, our vision is limited because of our very own atmosphere. Why? So if you look at this image, you can see the visible spectrum in the middle. And so I should explain what this image shows. So this is the opacity curve. How opaque the universe is to a certain wavelength of frequency, right? So if you look at this picture, you'll see that at the short wavelength range, it is mostly opaque to gamma rays, X-rays, UV, right? And that is a good thing. Our atmosphere lets in a bit of UV and that gives us skin cancer. Imagine what would happen if it let in most of the gamma rays and X-rays. Humanity and most plant and animal life would not exist, right? Okay, so infrared is also not visible to us. Why is it not visible? I am sure we've all read in school that how water vapor, methane, carbon dioxide, all these gases absorb infrared radiation. That is also related to the greenhouse effect and global warming, right? So thankfully, the radios can actually penetrate, right? So we know that wavelength, if the scattering particle and the incoming radiation wavelength are of the similar size, it can get scattered. But radio wavelengths are huge, right? So they can easily penetrate to the atmosphere, and we can observe them at the sea level. And we have so radio was the first out of all the invisible spectrum that we actually used to build telescopes, right? In 1930s, 40s, near the Second World War. And now we can build huge radio telescopes, radio antennas, and observe the sky in radio. Okay, so our vision is limited. What can we do? So our vision is limited. So look, we cannot do anything about the sun. But what we can do is that we can bypass the atmosphere. We now have the technology to put telescopes above the atmosphere into orbit around Earth. And from there, we can try to see in the invisible radiation, right? Okay, so in short, what multivalent astronomy is, electromagnetic spectrum is not visible. Most of the electromagnetic spectrum is not visible to us from Earth, except for radio. So we have to put telescopes out there above the atmosphere. And multivalent astronomy is observing the universe in the invisible part of the electronic spectrum and trying to make it visible. Okay, so astronomy before Second World War. So we have all read about Aryabhatta, the Bhaskara, and the Indian astronomers. There were ancient Chinese and Greek astronomers. There are even Mesopotamian astronomers who invented astronomy and astrology, as it is said. So all these great astronomers had was only the naked eye. They used the naked eye to painstakingly, at every night, they would go out and observe the stars. Some of the stars seem to move, they call them planets. And all these things were done by them, right? They identified all the constellations. So there was a huge gap. So you see, maximum it was 500 AD, 500 CE, right? Then 1,000 years later, comes along Galileo and Newton. They invent the first telescopes. Galileo, the first refracting kind, and Newton, the first reflecting kind, right? And humanity gains a new eye to say, right? To look at the universe. This is again optical, nothing extraordinary, but they gained the ability to see the universe using telescopes, right? And now let's come to 19th and early 20th century. We have legendary astronomers like Annie Jump Cannon, Arthur Eddington. Arthur Eddington, you know that he was the main person who proved, as well as to say, Einstein's general theory of relativity. And of course, we have Hubble, right? So these people now in the early 20th century, these people had massive observatories, huge, 40, 50 feet telescopes, best in the world, right? And these people used them judiciously and they used them very well. That's why we are talking about them, right? So they used them to unravel a lot of mysteries of the universe. But think about this. Everything up till now, up till the early 20th century, is still in the optical. Everything that we are doing, we are talking about these great astronomers. Now, I mean, you can just pull out your phone right now and type in pretty pictures from JWST, right? You'll get this 8K huge resolution images. Think about what a privilege we have right now. These great astronomers, throughout human history, no one has had that privilege. I mean, it's mind-blowing, right, to think about it. Okay, so a quick timeline of multivalent astronomy. So as horrible as the Second World War was, it meant that armies needed to understand how planes are moving. They invented radar, right, using radio wavelength. And they also needed to build faster, stronger planes that gave rise to rocket science. So in 1937, the first radio telescope was built. It was just on the eve of the Second World War, right? In 1946, comes along the great American astrophysicist Lyman Spitzer, and he proposes that our rocket science is evolving. We can build faster, stronger planes. There should be a time when we can put. He was talking about optical, obviously. He was talking about that we can put a huge optical telescope above the atmosphere. See, the atmosphere has another horrible property, right? So atmosphere has turbulence, and that turbulence causes whatever we are observing to get blurred. So we can completely eliminate that effect if you could put a telescope in space. Okay, so 1957, humanity enters space age with the launch of Sputnik 1. Then comes along OA2 and Orion 1. These are the first UV telescopes and first proper telescopes to be put into space. Then comes along the various X-ray, IR, and microwave other satellites. And finally, in 1990, Lyman Spitzer's dream comes true, that we put a large space telescope into space, a huge optical telescope, and it completely changes astronomy forever. I mean, before JWST, any picture that you have ever seen, not any picture, I mean, most of the pictures that you have seen of space have probably been from Hubble. Hubble brought the aesthetics, the beauty of astronomy out in its full glory, right? Okay, so we started the talk with a picture of the sky. So here's the sky at multiple wavelengths. So the thick band in the middle is the galactic disk of the Milky Way, right? The same thing observed at infrared looks very different. Same thing observed at radio looks even weirder. And finally in X-ray, completely looks, mind blowing, right? So we'll learn a bit about what these things are as the talk goes on. Okay, so what I'm going to do is that I'm going to show you 3 examples and try to convince you that we do in fact need multi-wavelength astronomy. So what better way to start than to talk about the star in our backyard, the sun. So if you look at the optical image, this is an actual true optical image. So what we see of the sun is basically a bit of the light gets scattered, right? The blue light gets scattered. So, but if you could put a telescope out there in space and take the picture, it will look white mostly. Okay. So if you look at the optical picture, the sun is, well, bland, to say it plain, to put it bluntly, right? So there is not much activity going on. But if we observe the sun at different wavelengths, what do we see? We see infrared. There is the sun with some activity, and there are huge black cavities, right? If we look at ultraviolet, we'll see the sun is extremely active. It's not bland at all, and there is ultraviolet radiation coming out of, and there are, you can see spicules and other stuff being thrown out of the sun, right? In radio, mostly we'll see the effect of magnetic fields in the sun, and in X-ray we see something which is called the corona, right? What is the corona? If you've ever seen a picture of the solar eclipse, you'll see when the sun gets blocked out, there is a beautiful crown-like radiation that is coming out from the sun, right? So that is referred to the corona. Now, corona is a very bad word to say after 2 years of COVID, right? But the solar corona is magnificent. And there is a thing, right? I mean, the solar corona is very important, as in, think about this. What is the temperature of the sun? 5,500 Kelvin, 6,000 Kelvin, right? That is the surface of photosphere. That is a black body, right? But does anyone know what the temperature of the solar corona is? It's 1 million to 10 million to 10 million Kelvin. How does a thing that is radiating at 6,000 Kelvin heat up the corona to 1 million or Kelvin, right? So that is known as the coronal heating problem. So we all this we know now because of multi-wavelength astronomy. So this is a very nice picture from NASA. So what it shows is that at various wavelengths, how the sun looks, and what are the why does the sun look different? This is the main question. Why does it look different at all at different wavelengths? Because there are different processes going on in the sun, different emission mechanisms going on in the sun. Sun is not a monolith. There isn't just a black body emitting stuff, right? So there are many processes going on, and you can see it's written, right? So 10,000 Kelvin at 1600 Angstrom, you can see the upper photosphere, surface of the sun, right? Then you have the chromosphere where most of the UV comes from, and then we have the 1 million Kelvin hot corona that is flaring, right? And then we have 10 million and even hotter and hotter coronal emission, right? So think about this. I mean, if we only looked at optical, that's what we would see, just that. If we did not use any other waveband to look at the sun, our knowledge would be incomplete, to say the least. Okay. Another thing. So if you, so this is an image from the VLT in Chile. So if we looked up in the sky, I'm not exactly sure in which part of the sky, but 500 light years from Earth, you'd see a big void in space. Now, what is this? A Bermuda Triangle in space? So, I mean, think about this. This is not a diffuse thing. This is a very well-defined edge. This is not I mean, somehow the stars are moving away due to gravity or something. It's not like that. It's a very well-defined edge. And I don't know if you can see, but if you look closely, inside the edge, around the edge, the stars appear redder compared to outside. Right? So what is this? Now, this is optical image. This is what we naturally see if our eyes were as powerful as telescopes, right? Now let's look at it at infrared. So this is the new technology telescope operated by ISO at Chile. So what you'd see is this. It's not white at all. So what is this? What is this big black blob that is floating around in space? So these are stellar nurseries. These are so-called stellar nurseries. Stellar nurseries are, these are not the actual name. The actual name is a molecular cloud. So these molecular clouds are the stellar nurseries. These are very cold and dense molecular clouds. And these things, when they become gravitationally unstable, right? So they collapse. And these things, so this particular one is called Barnard 68. This is a molecular cloud, and it is twice as heavy as our sun. So when it collapses, it will give birth to a new star, right? So if we look at optical, we wouldn't know anything. And see another thing, why do we see it in where do we see the stars in the background? These are all Milky Way stars. Or every star that you see here is a Milky Way star. But some of the Milky Way stars are blocked out, right? So why do we see it in infrared? We have read Rayleigh scattering, right? The shorter the wavelength, the more scattered it gets. So longer wavelengths can pass through the molecules, right? Molecular cloud. That's why we can see it in infrared and not in optical. Okay. Another one. This is the M81. This is a grand design galaxy, right? So it's a very beautiful galaxy. So these are from different NASA operated telescopes. First one is infrared from Spitzer. Second one is from the Chandra X-ray Observatory. Third is obviously Hubble, and finally GALEX. This is a UV. This is a UV telescope, right? So look at the picture very carefully. In every picture, you are looking at the same thing, but it looks wildly different. In infrared, you can make out the galactic disk and the spiral arms. But infrared, what do we see? We see mostly emission from dust. The dust that is present in the galaxy, right? So that scatters UV and optical to longer wavelengths in infrared, right? If we look at in X-ray, we see that the galaxy is invisible. The galactic disk is completely invisible. What we can only see is the bright central core that is glowing brightly, and there are a few dots here and there within the galaxy. So what is this? This is coming from the nucleus. This is what I'm going to talk about later. Active galactic nucleus, right? So this galaxy is active. Its nucleus is emitting a lot of X-ray. There is hot gas around the nucleus, and the small dots are probably X-ray binaries. X-ray binaries are small black holes that are rotating around other stars and feeding off of the star, right? And it's glowing brightly. If we look at optical, most of the emission is coming from starlight. The normal starlight that we have, that is glowing, and it is very uniform. Out of all the pictures, the optical is very uniform. So if we look at the optical only, we get a sense, oh, M81 is a very uniform galaxy, nothing much is going on. But that's not the case at all. And finally, in UV, what we are seeing is the young, bright, hot stars. These are young stars, and they are glowing very brightly in the ultraviolet. And these are called the star-forming regions. So if we look at the UV picture, we can pick out the regions which are actively forming stars in the galaxy, right? Okay, so here's a panchromatic combined image. So this is what we should be seeing if we had access to the whole electromagnetic spectrum. But our view is limited to only that green picture, right? And that's that's not fair. Okay, so I hope that I have been able to convince you that we do in fact need multi-wavelength astronomy. Different astrophysical processes in different systems. We looked at a molecular cloud, we looked at a star, and we looked at a galaxy, right? So different astrophysical processes in different astrophysical systems emit at different wavelengths. An astrophysical object can appear wildly different if we look at in a single wave band compared to the other, right? And essentially, the knowledge of every astrophysical object and the universe by extension would be incomplete if we only looked at optical. Okay, and we conclude Act 1 and enter Act 2, the first LEAP astrosat, India's multi-wavelength eye in the sky. Okay, so again, a quick timeline. So this is the space program timeline of India. So S.K. Mitra, who was a student here at Presidency College in the early 1910s, 20s. So he used to conduct ionosphere experiments using radio right, radio wavelength. That had already been established. Jagadish Chandra Bose, you all know, he was a pioneer in that field. So he used to do that using that in Kolkata, here in Presidency, right? So 1969, ISRO is created under the leadership of Vikram Sarabhai. 1975, Aryabhatta 1 is launched about a Soviet rocket, and it becomes the first Indian satellite to enter space. So there is a reason I called this act the first leap and not the first step, because the first step had already been taken in 1975, because Aryabhatta 1 actually had X-ray detecting instruments on board. So it was technically the first X-ray astronomy in satellite that India had launched. Okay, so through the 1980s to up till 2000, India builds its own rockets, launches many satellites and space missions. You all know that ISRO is one of the most cost-effective, with a great record. It's very cost-effective and it has a great record in sending satellites into orbit, right? So 2008, India successfully launches its first lunar mission, Chandrayaan-1. We are all young back then, I'm sure, and you all remember it somewhat, right? It found evidence of water on the moon, right? 2013 comes along, and India launches Mangalyaan-1, the first Mars mission of India, and it is completed successfully. It does a lot of great work. And finally, 2015 comes along, and India launches its first multi-wavelength astronomy satellite, dedicated wholly. See, all the satellites before that, when none of them were astronomy satellites. Some of them did some space science, some of them did earth sciences or communications. INSAT is very famous for communications, right? So, and Chandrayaan, Mangalyaan, all these things were for studying planets in our solar system. But the first one that is completely dedicated to astronomy, that is AstroSat. So it was 7 years ago. So this is AstroSat at ISRO before launch. This is the actual payload that was launched about the PSLV C-30 rocket. So PSLV, some of you may know, is called the workhorse of ISRO. It is very reliable. So what you're seeing here is the payload, right? So the black thing is the solar panel that is folded out. When this payload goes into the space, the solar panels come out, and that will continue to power the satellite. And what you can see, the gold foil wrapped things are the imaging instruments. So you can see some pipe-like things, right? So 3 pipe-like things. They are the 3 two telescopes. One is a twin barrel telescope. And what you can see, like box-like things, right? Beside the imaging pipes, right? So they are another X-ray detecting instrument called LAX-PC. We'll learn about these things as we move along. Okay, so here's AstroSat at a glance. It was launched on 28 September 2015. It was 1,500 kilograms. It's quite heavy, but not as heavy as other satellites that have been launched. So ISRO did a perfectly good job of launching it into orbit. So it orbits at a height of 650 kilometers above the sea level in a near equatorial orbit, right? And there are 5 scientific instruments on board. Are you able to see the names of the instruments?
Yes.
Yeah, right. So there are 5 instruments. There is the Large Area Except Proportional Counter, LAX-PC. They are those boxes that I was talking about, right? Around the telescopes. So they detect hard X-rays. X-ray with huge, the photons are highly energetic, those X-rays, right? And then there is a soft X-ray telescope. This is an imaging telescope. LAX-PC does not take any images. So it actually takes images of sources, right? There is the CZTI, which observes very hard X-rays with extreme energy, right? And there is the ultraviolet imaging telescope in blue. The twin barrels that are you can see in the middle. That's the UVIT. That's one of the best ultraviolet telescopes that is currently in space, and that is from India, right? And finally, we have the scanning sky monitor. That thing actually, that is not exactly very important. That is normally not mentioned in most cases. What it does is basically it is always rotating in various directions and tries to look for it. It also observes in X-ray. It tries to look for X-ray sources which are transient. So what is transient? Transient means, the source appears and few moments later, it's no longer there. So they are most likely from various kinds of supernovae, gamma ray bursts, right? So it tries to identify those sources. Okay, so it was launched 7 years ago and it's still going strong. There have been some minor hiccups along the way, but AstroSat is still going strong. Okay, so AstroSat is a true collaborative effort. AstroSat wasn't just built by ISRO, the myth of a lone scientist sitting somewhere in his or her office and writing the equations down and then completely coming out eureka and completely changing the world. That is not true. It wasn't even true for Einstein and other people, right? And it is not true. It is certainly not true today. So AstroSat is a collaboration between various institutes. Obviously, the leading institute is ISRO. It is helped by the Indian Institute of Astrophysics, TIFR, and IUCAA. And there are international partners also. So Canadian Space Agency is a big partner in building the ultraviolet telescope. University of Calgary developed the software for that is also a Canadian university. It worked with the CSA and Indian Institute of Astrophysics to develop the software for the UVIT. And finally, we have University of Leicester. They helped build the soft X-ray telescope. So Leicester actually helped build another NASA telescope. There is, I don't know if you know, there is one particular astronomy mission which is very much like AstroSat. It's called Swift Observatory, right? So Swift Observatory had a XRT, X-ray telescope, right? So, and that was built by University of Leicester. So they have a great experience in building those things, right? Okay. So as I was saying, AstroSat is the product of hard work and dedication of hundreds of scientists, engineers, researchers across different institutes around the world. And finally, another thing, I mean, okay, scientists, engineers, that's fine. But students and young people like us are very important because, see, you can sing, you can be the world's greatest singer. But if someone is not there to appreciate your singing loses some of its value, right? So if there aren't young people to take up the mantle, so as to say, and take this forward, AstroSat forward, so AstroSat would lose some of its glory, right? But that has not been the case, and I'll talk about that. Okay, so quick look at all the instruments on board. So this is the ultraviolet imaging telescope. There are twin barrels, right? So one observes in the far UV range. Far UV is the part of the electromagnetic spectrum closer to X-ray than to optical, right? And another observes in near UV, just above the blue-violet visible range, right? And it also, the NUV telescope also observes in visible range. So what is so good about UVIT? Why I was telling that UVIT is one of the best UV telescopes up there, right? So most of the telescopes that observed UV that were up there, right, they're mostly gone. I mean, Galax was the premier UV telescope of NASA, but it has been a long time since it has stopped working. So UV, it has a very good spatial resolution. That means that it can identify sources. If two sources are very nearby in a poor spatial resolution telescope, they would appear to be a single source. But that is not the case for UV. UV can correctly identify that they are two different sources. And it has a huge field of view, half a degree. Think about this. Most telescopes have small field of view, good resolution, or bad spatial resolution and a large field of view. UV has a large field of view with a very good spatial resolution, right? And it can also do some spectroscopy, but it is not so good. Okay, now we come to the soft X-ray telescope. The image on the far left, far right, I guess. So my right. So that is the actual image of the soft X-ray telescope. So what you can see is actually it looks like an airplane engine, right? The top thing. So what it is actually is there are conical foils, concentric foils. So X-ray telescopes do not operate like normal telescope. UV and optical, you can actually have lenses, proper actual lens. You can just grind the lens into perfect shape or reflect it with a mirror. But X-ray doesn't work like that. So you have to approximately make a parabolic shape with these this is the soft X-ray telescope, right? Okay, so it has a good resolution, moderate resolution of 2.5 arc minutes. It observes in 0.3 to 8 kV, right? So is everyone familiar with how we interpret frequency as energy? Does anyone have any problem? I mean, so think about this. I mean, if you know the frequency, you can just multiply with it with the Planck's constant, and you can get the energy, right? So this is the energy equivalent of the frequency. So this is the soft part. That means that the X-rays are closer to UV than to gamma rays, right? So it has good timing resolution capabilities. I mean, timing. What does timing resolution mean? It means that you can get a readout of the data from the telescope in quick succession, in after a few seconds or few minutes, right? So that is important for sources that are whose brightness is varying very fast. You can understand those sources pretty well with this telescope, right? And it takes great images. I'll show an image I made yesterday. Okay, now we come to the large area X-ray proportional counter, LAX-PC. So it's the LAX-PC, the box-like thing that you saw, right? So it has xenon gas filled inside it, and it has many wired mesh layers. So the X-rays hit the thing, and so it basically counts X-ray photons hitting its surface. It does not try to take an image. It's just an proportional counter, right? So what's so special about LAX-PC? LAX-PC is special because there are three boxes, right? So this is not just a single box. Is not just the LAX-PC. There are three boxes. They make up the LAX-PC, and the effective area of these three boxes is 6,000 centimeters squared. I mean, I will tell you later. I mean, I'll show you actually that there was one telescope called RXT, which was the Rossi X-ray timing explorer, I believe. So it was launched by NASA, and it had an X-ray proportional counter, but it doesn't come anywhere near to LAX-PC in terms of its effective area. So it's pretty great. It observes in harder X-rays. You saw that SXT was observing in 0.3 to 8, and now we have 3 to 80 keV, right? So it observes in hard X-ray. It does not have a good spectroscopic property, but it makes up for that using its excellent time resolution. So it can actually, you can actually take out the data within microseconds. So it can do microsecond time resolution, right? So it is very well suited for sources which are varying very fast. That is varying 50, 60, 100 times in 1 second. You can study those sources using the LAX-PC. Finally, we have the CZTI, the cadmium zinc telluride imager. So cadmium zinc telluride is a material that you can use to detect hard X-rays. So it basically is like pixels, right? So if we arrange up a few pixels in a grid, so it's basically like that. So it operates in 10 to 150 keV. It has a huge field of view, right? And angular resolution of 8 arc minutes. And what it is mostly used for, I mean, I'll show you that the CZTI has been a great instrument. So when it started out, CZTI was, launched about AstroSat. The software was not ready, and people were blaming CZTI for all sorts of things, right? But what has happened since then, that it has emerged as a great player in identifying gamma ray bursts. And in some cases, it can also do the polarimetry. Polarimetry, you know that if you study the polarization of light, you can tell something about the electric and magnetic fields of its origin, right? So we can study the magnetic fields from the gamma ray bursts, right? Okay. So how good is AstroSat? I mean, there is Hubble, there is Chandra, there is this, there is that. There are many satellites. So one thing you have to understand: there are two types of satellites. One type is paradigm shifting, that completely shifts the whole view of astronomy. That's like JWST, Hubble, Chandra. These are, and you have to put in money for that. You have to put in $1 billion or more, tens of billions of dollars to build those. Because why do you need the money? Because you have to develop new technology. That technology doesn't exist. You have to put in money. You have to develop the technology. You have to build the telescope. You have to send it to space, right? So that would have been risky for India. India has never launched an astronomy satellite, and it would have been a blunder to try to do that. What India did instead was a very smart move. That was to, okay, we can build moderately useful telescopes, We can put a bunch of them together in a single observatory and we can launch it in space. So that will help us see the universe in multiple wavelengths at the same time, right? So that is a great thing about astrosat and the instruments specifically. So like I said, that LAXPC has a significantly large area for collecting X-rays than similar instruments on board RXT, for example, which was launched by NASA. And LAXPC has microsecond time resolution, which is unparalleled in LAXPC's field, right? LAXPC is a sole player there. And it is perfectly suited for studying very fast varying X-ray sources, right? Like X-ray binaries. And CZTI is one of the best instruments for detecting GRBs, gamma ray bursts, and measuring their polarization of hard X-rays. And what has happened was that, so CZTI has some defective pixels, right? Which do not operate to their optimum potential, right? So some clever people have designed a software, and now they can use those defective pixels to actually increase the range of detection into mega electron volt scale. I mean, think it was in GeV, keV scale, right? So now they can detect some GRB radiation that can go into, I mean, if that radiation was coming and hitting the CZTI, it would have spilled out into the other pixels and completely washed out the image, right? But since the pixels are not working as intended, the light, the MEV scale light is not spilling out, so as to say, and they can correct for that using their software and detect in MEV scale, right? So CZTI will be overtaken because NASA has launched a X-ray polarization IPXC, I believe, last year. So that is going to be better than CZTI, but CZTI is still great. Okay, how good is UVIT? So for the others, I had to tell you how good it is. For UVIT, you can see how good it is. So this is NGC 2336. This is again a grand design spiral galaxy. It's a beautiful galaxy. This is a Hubble view. And what you can see here is that the bottom panel is from the NASA's X-ray telescope, GALEX. GALEX was the paradigm shifting UV telescope. And on the top panel, you can see UVIT. And it's clearly visible that UVIT is much better than GALEX at taking pictures and doing other stuff, right? Once more, so this is from Andromeda Galaxy, the nearest galaxy to us. So again, this is a galaxy picture of a small star cluster within the Andromeda Galaxy. It looks like a blob. You cannot make out the individual stars and stuff, right? With UVIT, you can do that, right? So there is a great project going on led by the Canadian people, right? Canadian collaborators. So what they're doing is that they are actually cataloging the whole of Andromeda Galaxy, and they're every day they are finding new sources in Andromeda and cataloging them using UVIT. Okay, so astrosat is good. We now know that, but what has astrosat achieved, so as to say? So astrosat has achieved a lot of things, but I'll show you just 3 results. So it has witnessed the live formation of dwarf galaxies with UVIT. So what is live formation? I mean, see, our view of the universe is that smaller clumps of matter clump together to form bigger clumps of matter, right? So this is called a bottom-up view of the universe, right? So what astrosat has seen is that using UVIT, it has seen that matter, I mean, small clumps of gas and stars are coming together to form dwarf galaxies. That hadn't been seen before. So it has been so impressive. It has been a Nature paper. It came out this year. The same team, it found light from galaxies forming stars when the universe was half its age. It's 14 billion years now, right? So you can imagine it's even actually much younger than half its age, right? So that is also a Nature paper. You can see the galaxy that they found. You're familiar with Lyman radiation, right? I mean, Lyman, Balmer, that series. So Lyman is emitted from hydrogen, right? So what they found is that so when the stars are forming, they're emitting huge radiation, right? So that radiation is not visible mostly. Why? Because the universe is the gas in the universe is mostly hydrogen. So the gas in our line of sight to that galaxy absorbs most of that Lyman, right? And our galaxy itself is filled with hydrogen gas. That also absorbs a lot of the Lyman radiation, right? So that is actually, if you go out and look, So UV telescopes are actually pretty poor things. I mean, so you can take brilliant pictures with X-ray, with optical and other things, but because UV is absorbed by hydrogen so much, and hydrogen is so ubiquitous, so UV telescope don't take good pictures, are not that great, right? But UV has kind of changed that view. Okay, what has CZTI achieved? CZTI has seen over 500 gamma ray bursts. And remember, every gamma ray burst is probably from a supernova, and that means a supernova that is from a star so massive that it is exploding and probably will form a black hole. So it has probably witnessed 500 black hole bursts. So this is again unparalleled, and it has done some polarimetry studies on many of them, right? So okay, so this is from this slide is from my supervisor Ritaman Chatterjee, right? So what this slide shows is the how many people are using AstroSat, how many astronomers are actually using AstroSat, and what impact it has had on the Indian astronomy community, right? So what APPS stands for is the AstroSat proposal system. So what is a proposal? Let's say you want to observe a source in the sky, right? So what you have to do is that there is a website there, you have to go register yourself, and you have to write down a proposal that, okay, I want to observe that source. Why? Because this science can be done from what we'll see using AstroSat, and that's why I should be given time, right? So you can basically do that, and there are currently 2,000 accepted APPS proposals have been accepted. And I'm very happy to say that one of these proposals have been by a graduate student of this department, Abhinanda Chakraborty. So she has been, she has actually observed 6 galaxies with her proposal, right, using the UV. Okay, so more than half of them are Indian users from various Indian universities and institutes. There are nearly 900 international users, most of them from the US. So AstroSat is not just a local satellite. I mean, it's not just used by Indians. It's an international proper astronomy satellite. Okay. Universities is in bold because, well, we are at Presidency University, a state university, right? So 300 university proposals have been accepted, right? So many people from universities, like I mentioned, even graduate students like Abhinanda, they are writing proposals, getting time and observing astronomical objects, right? So there are ISARs, IITs, NITs, and other institutes. So all in all, AstroSat is going great. This is probably the most important slide, I would say, in this whole talk. So what has been the impact of AstroSat on young astronomers? Okay, 100 peer-reviewed papers have been written by astronomers from Indian universities. Think about this. Over 100 papers in the last 7 years have been submitted to peer-reviewed journals and accepted and published. And think about this, when you're talking about universities, of course, there are professors. Of course, there are great scientists, but there are a lot of young researchers, some graduate students, some PhD students, some even undergraduate students who are actually doing real research using India's first astronomy satellite and publishing those results. Think about this. How inspiring is that, right? So, yeah. So, in most of the AstroSat workshops, most people are from Indian universities, and most of them are young people like you, right? So 20 PhD theses have been completed related to AstroSat, and trust me when I say more are coming, right? So 25. So ISRO has a program, right? So like Moitro mentioned that I work on a ISRO-funded AstroSat project, right? So what ISRO has done is that it has over 7 years, AstroSat has collected a lot of data in various using various instruments, right? So there aren't enough scientists in India to process and study that data, right? So what they need is young people like us. So what they have devised is a program called AstroSat Archival Data Utilization Program, and they fund the students. They pay them junior research fellowships and senior research fellowships. So currently 25 projects are going on, where students, young people like us, are actually using archival data from AstroSat to study various astronomical objects and astronomical phenomena, right? And many of these projects will actually be turned into PhD thesis, and so the number of PhD theses is going to go up, right? And I mean, 25 is just a number that we have right now. I mean, more are going to be added to this. Okay. So in short, India AstroSat has completely changed the face of Indian astronomy. I mean, see, just being a good satellite, it's okay, that's fine. But being the first satellite and inspiring young astronomers and giving out excellent results, actually competing with international satellites. So AstroSat has done that, and that has ensured that it will have a lasting legacy in the Indian astronomy community, right? And most importantly, AstroSat has defined a generation of young astronomers in this country, and I'm hopeful some of them are sitting here today, right? Okay. So another impact of AstroSat is that AstroSat was the first astronomy satellite that India launched, right? So it has gone great. We can be hugely proud of AstroSat. Now it's time to look forward, right? So what plans does the ISRO and other institutes and Indian astronomers have? So next year, probably during May, I believe. So India is going to launch its own solar probe, Aditya L1. Yes, we had a talk from the chairman of the science working group, director of Aries, Dipankar Banerjee. He gave a talk last month here at Presidency. So so I was talking about the coronal heating problem, right? So that sun's corona is 6-7 times. I mean, not 6, 7, 3, 4, 5 times orders of magnitude hotter than its surface, right? So why is that? Maybe Aditya will tell us, right? So we've heard about the Parker solar probe. You may have heard about SOHO. These are NASA satellites. We hear about them. Now we will have our own solar mission, and it will what it will do is that it will create a bunch of young solar physicists in India. A lot of young solar physicists are going to come up in the next decade, right? So again, there is ExpoSat. ExpoSat is going to be the spiritual successor of the CZTI. So this is going to be used for looking at gamma ray bursts and other stuff, right? So work has already started on ExpoSat at Physics Research Laboratory and at ISRO. And then we have a great thing. This one is particularly my favorite. This is Daksha. Daksha is being proposed by IIT Bombay. So what it will do is that, so you all know about gravitational waves, right? In 2015, gravitational waves were first time observed, right? So what Daksha is going to do, so LIGO India is going to come up by 2030, hopefully. So when LIGO India comes up, there will be 3 LIGOs, and we can actually get pinpoint the place where it's coming from the sky, right? So I mean the gravitational wave is coming from, right? So what Daksha will do is that just as soon as LIGO sees some gravitational wave signal, Daksha will immediately follow up that signal to see if we can see some electromagnetic signals, which correspond to that particular gravitational wave signal, right? So Daksha is being proposed, but it requires some technology that doesn't exist on Earth. So it's going to be tough. So hopefully we'll see Daksha. And there is going to be INSIS. This is a screenshot of a paper by the director of Indian Institute of Astrophysics, Annapurni Subramanian. So what India is planning, ISRO is planning. So you remember that I told you that UVIT was a collaboration between Canadian Space Agency and ISRO. So they're taking this collaboration even further to create the next generation UV telescope. This is going to be a sole UV telescope, not a multi-wavelength satellite, just next generation telescope. With the UV is already great, but we can probably do much better, and we can even add good spectroscopic instruments. UV doesn't have good spectroscopic instruments right now, so we can do UV spectroscopy using INSIS, right? Okay, so all in all, the next decade is probably going to be great, and many of you will probably, hopefully, get to work on some of these instruments. Okay. So we arrive at part 3, the dark stars, active galaxies, and supermassive black holes, right? So it's a brief history of black holes. So why I chose the term dark stars is because John Mitchell and Simon Laplace, they had hypothesized in the 18th century about dark stars, right? So stars with such a huge gravity that even light may not be escaped its surface, right? So that happened. Then Einstein comes along with general theory of relativity. Schwarzschild publishes his description of event horizon. Penrose, Hawking, they talk about how black holes are a natural prediction. By the way, Penrose and Hawking's work was based on a work which was done by Amal Kumar Rai Chaudhary, who is a legendary professor here at Presidency. Right? Okay, so then Cygnus X1, the first X-ray source is that is identified that could be a black hole candidate, right? LIGO comes along in 2015, observes gravitational waves, and in 2019, Event Horizon Telescope publishes the first image taken by humans of a supermassive black hole, right? Very next year, Roger Penrose, Reinhard Genzel, and Andrea Ghez, they win the Nobel Prize for black hole science, right? Genzel and Ghez, they are actually astronomers, and they won because they actually found proof of the supermassive black hole at the center of Milky Way. What they did was that they observed the orbits of stars, which are moving very fast near a place that seems empty in the optical regime, right? So that is actually the central supermassive black hole of our galaxy. Okay. Finally, active galaxies. What are active galaxies? So there are many billions of galaxies across the universe. Some of them are active. What does active mean? Active means they are very bright. The core of these galaxies, as you can see, is very bright compared to the spiral arms, right? And these galaxies are active because they are actively accreting mass. The central supermassive black hole that is sitting at the center, it is actively accreting mass. The mass is falling onto the black hole, heating up and radiating a lot of light, right? So 10% of all galaxies are active. They have impressively bright core regions, and they can often outshine the host galaxy itself. In some active galaxies, the nucleus can outshine the whole galaxy itself, right? And another special thing, they emit over the long range of the EM spectrum, and they are perfect for multi-wavelength astronomy. Okay, so what is there at the center of the galaxy? So at the center of the galaxy, the nucleus of the galaxy is called an active galactic nucleus. So what they do is that they emit a galaxy's worth of light from a region few light days across. So the Kuiper belt objects beyond Pluto, light takes 6 hours from sun to get there. Multiplied by 4, you have 1 light day. Multiplied by 10, you have 10 light days. Seems like a lot of region, right? I mean, a lot of distance, right? Now think about this. The nearest star is 4 years away, 4 light years away, right? And there are 10 to the power 11 stars in the Milky Way. So how huge the galaxy is and how minuscule this region is. And this is emitting a galaxy's worth of light. What is happening, right? So some agents have massive jets coming out of them, right? So these are very fast-moving particles moving out of the black hole, right? These jets travel long distances. In short, agents are very fascinating, and they can be studied using multi-wavelength astronomy. Right? So, am I running out of time? Okay. So, agents are powered by supermassive black holes that weigh 1 million to 1 billion times the sun, right? Okay. So I'll show you pictures of one particular agent. This is Centaurus A. This is 10 million light years from Earth, right? So if you look at the Hubble Space Telescope image, so what you see is it's an elliptical galaxy, huge elliptical galaxy, and it has a lane of dust and molecular cloud across it, right? And when we observe it in different wavelengths, the view completely changes. If you saw the radio and the optical, you wouldn't believe that they are the same source, right? So in radio, you can see the huge jets that are coming out from the nucleus of the galaxy. In X-ray, you can see the hot gas surrounding the galaxy and the nucleus, and you can actually see the jet, right? You can see the jet that is coming out in X-ray, right? And in infrared, you can see the molecular cloud and dust emission, right? So this is the combined panchromatic image of Centaurus A, a visible X-ray, infrared, radio mixed together. And this is what the galaxy actually looks like. And we'd miss a lot of this active galaxy if we only looked at optical, right? So agents appear wildly different at different wavelengths. Okay. So now what about active galaxy research using AstroSat? So AstroSat view of active galaxies. AstroSat, like I mentioned, LAXPC has good timing resolution, right? So has is SXT, and UVT is also there. So AstroSat can be studied the short time scale. So one thing about these agent systems is that AGN systems actually vary if you look at the brightness of AGNs, right? So over time, it varies in every time scale. From minute, if you look at, if you take pictures of an AGN every minute and, get out the number that is the brightness of the AGN at every minute, right? You will see that is completely randomly varying. And from minutes time scale to years and even decades, it is completely varying randomly. So this is a very unique system. Why is it happening? No other astrophysical system does this kind of stuff, right? So when matter falls into black hole, this kind of behavior is seen. So what we can do is that we can use astrosat to study this variation, time varying. These are time varying sources, and you can use LAXPC, SXT, and UV to study these short time scale variations. Okay, so these are the images that I made yesterday. These are image that is cooked up or something, right? This is an actual image that was taken by astrosat using the soft X-ray telescope and the UV of this galaxy, and you can see in X-ray you can only see the active galactic nucleus. It is completely dominating the view, right? And in UV you can see the central core AGN, and you can also see the galaxy around it, right? So you can see both the host galaxy and the bright AGN core, right? So astrosat gives us pretty pictures of AGNs, in short. Okay, if you're wondering how this galaxy actually looks in optical, I told you this is a nearby galaxy, right? So this is an extended object. So it has a dust lane in the middle, and there is the central AGN shining through in optical. Okay, so this is the US Stock Exchange data on my birthday this year. Okay, so look at this. This looks like something like a random walk system, right? So it is varying with time. The stock exchange every day. This is a completely normal thing. You go to the internet today, search for today's national stock exchange data for India, plot it up. It will look something like this. And this is 1 day data. You can plot a week-long data, month-long data, year-long data, decade-long data, and you'll see that it looks like a random walk behavior or something random behavior. So any data that varies with time and you can plot it up is called a time series, right? It's varying with time. So this is the type of data that economists and financial experts and those investment gurus, they are pouring over this kind of data, and they're trying to tell you what to do, where to invest, how to run the economy, right? So in short, time series data can provide a wealth of information about any system, be it an economic system, be it a physical system, or anything, right? So like I mentioned, AGN also shows this kind of behavior. AGN brightness actually fluctuates randomly throughout a day, throughout a week, throughout a month, throughout a decade, right? And what we can do is that we can use this time series data. By the way, so this is brightness, light, right? So this is light varying, so we call it light curves in AGN research, right? So light curves can tell us a lot. So what can light curves actually tell us about, right? So, okay, the brightness is fluctuating. Okay, fine. But what is actually happening? What is actually happening is that when this brightness is, fluctuating, so there was this slide, right? So look at this. So there is a black hole at the center. There is something called the accretion disk around it. What is actually happening is that matter and gas is falling into the black hole. It cannot fall in randomly. It has angular momentum. It has to lose that angular momentum. So it forms an accretion disk, and then it accretes onto the black hole. The black hole grows in size, right? Now, how does it fall in how does matter fall into the black hole? It has to lose that energy, right, to fall into the black hole. So the accretion disk actually heats up, emits that energy, and the matter can then fall into the black hole. So now, as the accretion happens, the accretion process is a random. There are accretion fluctuations in the accretion disk, and that is causing the accretion, the brightness of the accretion disk to fluctuate randomly. So that is what we can study by studying light curves. And it can tell us a lot about the geometry and the emission processes in active galactic nucleuses. Okay, so final two slides. So what kind of research is done here at Presidency? So there are two AstroSat funded ISRO projects here at Presidency. So a particular subclass of agents, right? Agents are like fingers; they come in all shapes and sizes. So particular type of agent in which the jet is pointed directly along our line of sight. The jet completely dominates our view of the galaxy, right? So they are called blazars. So blazars, like all other agents, vary at all different time scale from minutes to decades, right? Now the fundamental question about blazar is now that where does this variability originate from, right? So, and another question then comes to mind. So we know that accretion disks have fluctuations, and the brightness fluctuates. But is it related to the jet? I mean, the jet is also varying, right? Are these two things related, or are they not? If not, then where is the variability coming from in the jet itself, right? So all this type, and I mean, it emits a lot of radio emissions, so jets. And radio, we know, is where there is radio emission, there is probably magnetic fields, huge magnetic fields, right? So what are the emission mechanisms? What are the geometric structures? What are the magnetic fields in jets? These kind of questions can probably be answered in the short time scale. If you look at the short time scale variations of jets, and that can be done with AstroSat. So what you can see in the top is, well, the jet coming out of an artist's impression, right, of a jet coming out of a black hole accretion disk. And the bottom panel is actual blazar data. Blazar jet is varying with time, and that data plotted in cyan. This is of a very famous blazar called Markarian 421. So so we work with Professor Ritaban Chatterjee. He's the principal investigator of both these projects. And this particular blazar projects to see if disks and jets are connected is led by Sushmita Dash, who is the senior research fellow here. She's not here today. She's at Aries and Nainital. So there is a conference going on there. And this is what I do. Okay. So while researching for this talk, I learned that fluctuation studies in accretion disks fluctuate, and the people who study these things, right? So they came up with the term discoseismology. Seismology, as you know, is a study of earthquakes or variations in the ground, right? So variation in disks, and that study is called discoseismology. So as an aspiring astronomer and an aspiring discoseismologist, let me tell you about my work. So what I'm currently working on is So in some cases, the jets are not very prominent in AGN, right? And in some cases, they are almost non-existent. So in those cases, where is the emission coming from? Well, there is, of course, the accretion disk. And astronomers have come up with an explanation that there is probably a compact thing called corona. This has nothing to do with solar corona. This is another type of corona, which is a ball of plasma, which forms very close to the black hole. And most of the X-ray emission from an AGN system probably comes from the corona. And the disk mostly radiates in UV and optical, right? So think about this. The corona is not directly connected to the accretion disk. So what is happening? So as the disk is glowing, radiation is coming out from the disk, and it is probably reaching corona. And what we think is happening is that the corona has hot gas that upscatters. You have read about Compton scattering, right? Where light comes in, high frequency light comes in, and low frequency light leaves. So the inverse of that is called inverse Compton, where low frequency light comes in and high frequency light leaves. The light gains energy. So we think something like that happens. The UV is upscattered to X-rays. So what I'm trying to do is coming up with a model of accretion disk corona system, and these are actual simulated light curves that I've generated. So you can see these are random light curves, right? So they have the property of these look like actual real AGN light curves. And what we have here below is the actual data. The galaxy, remember that I showed you, IC43298, right? AGN. So this is actual time variability data from UVIT, LaxBC, and SXT. And what we can do is that we can simulate light curves, and then this is basically our theory, and we can test our theory with, AstroSat data. We can study how the AGN is varying over a single day. That is the short time scale fluctuations. Okay, credits. Most of the images I've tried to credit them all timeline related information I've taken from Wikipedia. All instruments images from AstroSat have been from this particular website. Note this down if you want to learn more about AstroSat. So you can go to this AstroSat website. You can learn about all the instruments. We can learn about the science support cell and how you can get involved with AstroSat. And there are some stock images from Getty and Flickr, right? Okay. So to quickly summarize the talk, different astrophysical processes emit at different wavelengths. We have to observe them in a multi-wavelength manner. Otherwise, we would learn about only few astrophysical processes, and right. So we miss most of the view of the universe, right? For that, we need to send telescopes into space. India has taken its first leap into space-based astronomy with the AstroSat mission. AstroSat, as I showed you, is a great satellite. It has completely changed Indian astronomy and has produced some great results. And finally, I talked about what active galaxies are and how we can use them to use AstroSat to study active galaxies. Acknowledgements are due. Sincere thanks to the Scientific Organizing Committee and Local Organizing Committee and all the volunteers that have come together to organize this year's Presision. And the next week, you're going to have the UG Symposium, right? So best of luck for that and all the other events. And sincere thanks to Professor Ritaban Chatterjee for providing the data regarding AstroSat's impact. And also sincere thanks to SC ma'am. And thank you. So time for questions, I believe, if you have any. I mean, I think most people are hungry for lunch. I mean, you can ask without a mic, I guess.
Okay, so now it's okay, so it's time for questions. So questions from audience.
Yes,
Okay, so
unique is there and yeah, right.
অপটিক্যাল ওয়েভলেন্থ লাইট ওয়েভ তো দেখতে পাই না আমরা অপটিক্যাল ভিজিবল স্পেকট্রাম এর অন্য স্পেকট্রামে যখন ইউজ করে আমরা ছবি নিচ্ছি তার কালারটা আমরা কিভাবে ডিসাইড করছি
কালার আমরা ডিসাইড করি না মানে দেখো মানে you have to realize something. Color is in our brains, right? There is nothing. A red light, what we say, a red photon is not carrying a flag saying I am red, right? That is how our brain interprets color. So all these colors are false colored images, right? So like all these colors, right? So these things you are seeing. Look at the radio image, right? So the color used here and the color used, these are the same radio images, right? But the colors are different. So we have to put in colors that we can see in the visible spectrum, right? And to distinguish multicolored, multi-wavelength images, right?
Okay, then I can just.
Yes, unique.
So, first of all, fantastic talk, thank you.
Thank you.
And second thing that was that we've seen the AstroSat is able to figure out the gamma radio burst and it is able to detect it. So, is it possible that we are able to detect the infinitesimal fast radio burst using the, or was there any history of its detection?
I have no idea about that, unfortunately, but there are people in IIT Bombay and I mean, there is one person at IIT Bombay, Divita. If you can find her contact, you can talk to them. So what I know about, particularly about CZTI is that what CZTI can do is that it can look at the sky with a huge field of view and it can see transient sources, gamma ray burst and other sources which are emitting in hard X-rays, right? That's mostly what it does. Okay. So what you can do actually is that you can look up the AstroSat website and go to the CZTI section and see if you can find information about what you're looking for, right?
Thank you for the nice talk. So might you say does AstroSat play any role in searching or tracking?
No, it doesn't. So AstroSat is not, say, when you're launching a telescope, it's not particularly suited for, see, it has to be suited for something, right? Otherwise, every telescope could do everything. We could use Aditya to do everything that AstroSat does, right? We can't do that. So what happens is that when you're looking for dark matter or things, you are mostly looking at galaxy clusters, right? So galaxy clusters have a lot of dark matter, right? And you can study the effects that those dark matter halos are having, right? So to do that, you need something of a survey-like situation, like SDSS did. Or there is going to be a huge telescope. India is a part of that 30-meter telescope. TMT is going to come up, right? So TMT is going to actually look for dark matter and other stuff. So astrosat is mostly used for looking at particular isolated astrophysical objects, not doing something at a galaxy cluster level, right?
Everybody has a question.
Why UVT is more important rather than the other parts of astrosat? I mean, ইউনিভার্সিটি কি আলটিমেট উইন্ডো দিয়ে দেখলে অন্যরকম স্পেশাল কিছু ব্যাপার
না, যেটা বললাম যে ব্যাপারটা হচ্ছে আমাদের গ্যালাক্সি হাইড্রোজেন গ্যাসে ভর্তি, রাইট? ইউনিভার্স মানে আমাদের মানে ইন্টার গ্যালাকটিক স্পেসটাও হাইড্রোজেন গ্যাসে ভর্তি। What happens is that most of the UV যে ফ্রিকোয়েন্সি, তুই ভেবে দেখ যদি হয়, সেটা হচ্ছে 912 হচ্ছে আমাদের লাইম্যান আলফা, রাইট? So around that ultraviolet, far ultraviolet, most of that gets absorbed by মানে neutral hydrogen absorbed করে ionized হয়ে যায়। সো ইউভিতে আমরা দেখতে পাই না মোস্টলি। ইউভি স্যাটেলাইট গুলো ওই কারণে ভালো, ইউভি স্যাটেলাইট এই কারণে ইম্পর্টেন্ট, এক্স-রে ক্যান পেনিট্রেট থ্রু ইজিলি, ইনফ্রারেড ক্যান পেনিট্রেট থ্রু, অপটিক্যালও হয়। কিন্তু ইউভিটা যেটা হয় যে আমাদের গ্যালাক্সির ভেতরে যে হাইড্রোজেন গ্যাস এবং গ্যালাক্সির বাইরে ইন্টারগ্যালাকটিক স্পেসে যে হাইড্রোজেন গ্যাস, সেটা অ্যাবজর্ব করে দেয়। ওই জন্য ভালো ইউভি স্যাটেলাইট এই কারণে ইম্পর্টেন্ট। আর একটা হচ্ছে যখন ইয়াং স্টার্স তৈরি হচ্ছে, তারা যখন ধরবি একটা হাইড্রোজেন অ্যাটম ফর্ম হচ্ছে, সে কি করবে? একটা ইলেকট্রন এনার্জি নিয়েছিল, সে যখন এলো একসাথে মানে বন্ড করলে একটা প্রোটনের সাথে, তাকে তো এক্সেস এনার্জিটা এমিট করতে হবে, এন্ড দ্যাট ইজ প্রবাবলি গোইং টু বি ইন ইউভি। তো সেই কারণে স্টার ফর্মিং যে মানে আর্লি ইউনিভার্সের স্টার ফর্মিং যে গ্যালাক্সি গুলো, তো সেইগুলোকে দেখার জন্য মানে ইম্পর্টেন্ট এই কারণে, রাইট?
Okay.
My question is, GRBs emit GeV emissions, but CZTI is used to detect hard X-rays. So how come it is used for studying?
See, GRBs do not only emit in GeV, right? So they also emit in a lot of wavelengths. So as hard as you can go, it's better, right? If you can observe in GeV, it's great. So there is a NASA telescope called Fermi, if you have heard about that. It does GRB, I mean, it observes in GeV scale, right? So we do not always need GeV emission to see in GeV. We can see in hard X-ray as hard as we can go, and that can also tell us about GRBs, right? So think about this. The most important property of a GRB is that it only stays for a few seconds to few minutes. If you can see such a source in hard X-rays, that is as good as detecting it in GeV, right? That's the thing. So first we have to detect it, and when we have detected it, fine, we can do some statistics to find out where the GRBs are happening in the visible universe. And what we can also do, if possible, try to study how the X-rays were produced, what kind of magnetic fields. I mean, see, if the star is there and a huge amount of material is being thrown out, right? Ionized material is being thrown out, there is a huge amount of magnetic field at play. So what kind of magnetic fields are there? What kind of things are happening? See, all this theory about black holes forming and these things we have never actually seen a star explode and form a black hole. And that cannot be seen actually, right? I mean, the time scales are such that we cannot see that. But the only way we can learn about these processes is by observing stuff like GRB and other stuff, right? So that's why these things are important.
Okay, so I think Sandra has a question.
Sandra herself gave a talk yesterday, right? Yeah, you can speak without mic.
So great talk, brother. So my question is, so for our galaxy, Milky Way, the galactic bouquet is currently inactive.
Yes.
So do we have any information on it being active in past, or is there any chance being?
Excellent question. See, were you present at that talk about circumgalactic material that was given by Sanskriti? Yeah. So if you look at the X-ray image of our galaxy, so this is the X-ray image, right? So there is something called this bubble-like thing you can see, right? That is emitting X-ray. This is called the Rosetta bubble, right? So there is another smaller bubble closer to the disk of the Milky Way, it is called the Fermi bubble. Some people think that this Fermi bubble is actually the remnant of when our supermassive black hole was active in the past, right? So we may find some signatures as more people are looking at these E Rosetta bubbles and Fermi bubbles, right? See, yeah. So this is, I mean, can you please repeat? So I forgot what you were asking. So, right. See, so what we are seeing is the variability of flux, and what we can infer from this, right? That's your question, right? So mostly what we believe is that, see, how the fluctuations happen. The fluctuations are random; they appear random, but the processes that are generating those fluctuations are physical processes, right? They aren't something magical things. So what astronomers have done is that they have developed models about how these fluctuations are generated. So what I should mention is that all that we know about accretion disks and this agent things are not very well understood. But the best model that we have is a thin disk of matter is rotating around a black hole, right? And matter is falling inwards. But there is magnetic. This is a disk of plasma, right? So there are magnetic fields, and magnetic field generates turbulences in the disk itself. And as the turbulence happens, the local accretion rate at any point on the disk fluctuates. It's a turbulent motion, right? It's a random thing. And as it fluctuates, the local temperature of the disk fluctuates. Think about this. The disk does not have a uniform temperature. Closer to the black hole, it has higher temperature, and more outward, it has lower temperature, right? So if the temperatures are varying, so UV is mostly produced from closer to the black hole, whereas optical farther from the black hole, infrared even farther from the black hole. So what we mostly do is that we'll try to look at these fluctuations at two different wavebands, in ultraviolet and optical, and do we find any correlation? If we find any correlation, then we can try to see how the fluctuations are actually propagating inward, if the fluctuations are at all propagating. If they're propagating, how the outward fluctuation is modulating the inward fluctuations, right? And how optical is causing, how the fluctuations that generate optical may be affecting the fluctuations that are generating UV. That kind of stuff. Basically, what we can study is the accretion fluctuations and the geometry of the agent system, right? That's what you can study using light curves.
Okay, so only one more. Maybe we can take only one. Okay.
I have a question regarding
মানে যার যা কোশ্চেন আছে এরপর তো মানে ভিডিও আমরা কথা বলতে পারবো। হ্যাঁ,
gold foil এখানে তো
আচ্ছা, গোল্ড ফয়েল, এটা এক্সেলেন্ট কোশ্চেন। তার কারণটা হচ্ছে গোল্ডের অ্যাটমিক নাম্বার জানি, আমি ভুলে গেছি, বাট মনে আছে কারো? ইটস এ ভেরি হাই নাম্বার, ঠিক আছে, গোল্ডের অ্যাটমিক যে নাম্বারটা, রাইট? সো গোল্ড ইজ এ ভেরি হেভি নিউক্লিয়াস, আর গোল্ড ইজ কেমিক্যালি ইনার্ট। গোল্ডকে অ্যাসিডে ফেলে দিলেও গোল্ডের কিছু হয় না। দ্যাটস হাউ ইউ টেস্ট গোল্ড if it is actual gold, right? Only particularly that thing called aqua regia can dissolve gold, other things cannot. So gold is chemically inert, it is extremely durable, and it has a fantastic property that you can beat it out into films and sheets, right? And it can reflect a lot of heat. So what it can do is that it can form a chemically inert, durable, light reflecting, heat reflecting shield, protective barrier for the telescopes. So the telescopes are going to be, see, if at the last moment when the satellite is being launched, there is no more rocket to protect it, right? So it is going to be rotating around Earth. So you need to shield it from other type of space debris, other kind of radiation. Solar radiation is extremely strong there, right? So for that, the best material to do that is, one of the best materials to do that is gold. Okay, so thank you everyone for turning up today.
Okay, thank you everyone. I want to thank Moitra Kundu for conducting this session. And I would like also thank to Arijit sir for his wonderful talk. I also like to take opportunity to thank our faculties for their continuous support for organizing this event. And finally, I would thank our audiences to come in this event after such a short notice. We shall update the further details of our next events in our website and social media handles soon and let you know. So please visit our website regularly. Thanks to all of you once again.